Uh, can you please confirm that my screen is visible and I am audible?
Yes, sir. Your screen is visible
Yes,
on
sir.
mute.
Thank you very much. Good evening, everyone. Extremely sorry for the late joining. Some urgency meeting. So the topic which was taken is like a generative AI. The most popular term or trending term in the current generation of AI, that is generative AI. Look at the what happened in the last few decades. There are many enhancements that are happening from the traditional AI, which we all familiar, to any advancements of AI. Maybe you can call like AI plus plus plus, where you can say the machine learning, deep learning, and natural language processing, problem solving, robotics, multi-agent systems. So many concepts are changed, and there is a variety of data formats also parallelly there are changes are there. So one side there's a environment in the algorithms, they're addressing the complex problems, and other side is the data evolution with the different kind of a data formats, including the multimodality kind of a thing. So that means there's a very good amount of work is happening in this area, and there are major changes are happening. And this is like a image which is given by the multimodal multimodal LLM that's called a Gemini. So which is actually there's given a input image. There's a input image, and then give a prompt like this: convert this image into a watercolor painting Scottney style. Now, actually, the LLM actually changed the complete output, is generating output. So you can see see from the face-to-face conversions are normal, right? That we can say some kind of a rotations, changes, and everything can be made. But here altogether a different thing. Maybe the kind of a reasoning out of coming from out of this one, maybe the kind of a color combinations, right? The color combinations, and maybe the somehow the like a texture. So those are actually taken into account while generating a picture of the requirement list. That means it is possible today to generate a new kind of a data. Let us see how the people are working with this kind of a analysis with the recently elected president elected Trump. So for his security, they use robotic dogs. So that means robotic dogs is patrolling the to safeguard the Trump. Here you can see there is a many of these the robot dogs which are continuously monitoring it, and now you see the kind of advancements which are happening. Normally we can able to see till something was there. Suppose if a big wall was there, maybe as a human I can see up to this one, but the dogs can actually take this from sensor output and able to even simulate. You can able to look at it, right? So that's what the people are using the technology for different kind of a purposes. So not exactly what is meant by generative AI. It's nothing but a set of AI methodologies that can produce a novel content which is almost look like a training data that was trained, that the algorithm was trained. So that's why you can say generative AI. It refers to a set of AI methodologies that can produce novel content that resembles the training data that they were exposed to. That means we have a kind of an algorithm, and there's a training data which is actually we trained, and now from this model, model actually generates another kind of a data which is actually similar to the training data, right? So that means the content could be something like a synthesizing it. Maybe earlier, maybe some of the people who are in the ECE, they might be studied like network synthesis and analysis, right? Similarly, we are looking for a data synthesis. The data could be a text, or it could be like a music or image, or even it could be a code. Some of you maybe heard recently the Google CEO Sundar Pichai has mentioned that 25% of the software was written by the AI agent. Okay, that means today you can also generate a code, and also of course along with the text, image, video, music, or any other kind of a modality. So that means it appears as good as the realistic manner. So now how these are happening? Because these tools are actually in the concept called taught to be used, right? So that means they actually, whatever that you trained, it mainly actually based on that one. In case if something was not trained, maybe of course you may not get a correct result. That's what we can say. There is always a possibility to do some mistakes that we call like a regressions, right? So now, if you look at what is happening here, suppose I have a huge amount of the training data. Normally, you may be seen here in these days, they talk about like a 540 billion parameters they train and a huge amount of data set, right? So now we have a large amount of the data, but is it like a correctly universally representing one? That we are not sure, right? So now is there any possibility to do multi-facet of this kind of a data? That means I can take all possible kind of a evaluation. Suppose you can take this is like a fruit. I can take multiple kind of a pieces, different kind of a structural pieces. I can able to come out of it, and maybe that I may use for training, right? So that's like a kind of a synthesizing it. So what McKinsey defines is this is the chat GPT kind of a generative AI algorithms can be used to create a new content, including the multimodal like audio, code, images, text, simulations, and so on. So now there's like a lot of breakthroughs are happening in this area to drastically change the what we approach the content creation, right? So that means you give some kind of a sentences, and then now you ask the LLM to give you some additional content, it will try to provide it. So now just see what is happening in the background. Normally, if you have a text data, the text or images, then they are actually built by the previously built model of the statistical distribution of the tokens, because you have these so many words over there, words or phrases, and you can see how they're distributed in the given sentence. And from that, you can create a very large data set that can be used for training the model. Now, essentially what is happening is that now the traditional AI, what we are having, the traditional AI takes the training data, right? And normally given a data is usually split into the training data and the test data. And this trained data is used to build the system, and test data is used to verify the system. Now you can see this is build the system is actually used for prediction models, right? We want to predict something. These models are useful. And of course, how good that model, we are using the test data. But now what we are doing is we are actually generating the data. So earlier, the models are used to predict the outcome. Now, or predict the target. Now, what we are doing is we are actually generating the data. Now, you can see, just slightly observe it. We started with the having a data. Now we are generating the data, right? So you can see that how the paradigm was changed, a lot of things. The earlier, the models are actually, we build the model based on the data and use for prediction, but now that prediction is actually leads to the generating the new data, right? So that's what the today's generative AI is taking place. So maybe there's a possibility that to do the mistakes by the limitations of this process, but most of the cases, maybe we may say that this is like a good approach to do that one. Now, again, step back and check that one, whether what we have started with the computer science, even the computers, to do the computation, right? And then we started writing the programming. So when you say giving a programming, we are know that on what we are actually expecting or what could be the specifications that are there. That means we are very clear what kind of input we need to give and what is the expectation from that program. So then we can easily write a program. Suppose, for example, you take a quick sort and we have the a given set of numbers in maybe in an array form, and we want to do the arrange the numbers in a ascending or maybe descending order, right? So that means we know the input, we know what kind of output that was known. So now that we can write a clear specification, that means we can write a clear program for that. Okay? But now the learning is slightly different from that, where in the learning, we don't have any clear specifications. Maybe everything is like a maybe imprecise or incomplete one, the specific intent. And then we can construct a function that satisfies the intent. Suppose you can see it could be like it looks like a cat, it looks like a dog, or it could be it looks like some other object. But we are trying to build a model. We are trying to building a model, and finally we are making the output of it. So that means Here, this model is actually learned from the data. So that is actually a difference between the programming and the learning. Now, what we are, for what purpose that we are using all these kind of a tools is mainly for the problem solving. So sometimes the problem could appear as a simple, or the problem could be a complex. Similarly, the solution which we develop, maybe it could be a simple solution, could be a complex solution. Okay. But there is a possibility that the problem may be appear as a complex, and you may get a simple solution also. And of course, the vice versa is also be possible. So now just take an example, which actually a US university got a project to find the trajectory of a star rocket's launching. Because in the star rocket launching, as we know that the same vehicle will take the multiple rockets into space, and then it will leave into the space. Each one is having a different kind of a trajectory. The problem which was given to here is to find the trajectory of each and every. Any questions? Okay. So to find the trajectory of each and every rocket. Now here, the problem actually a mission critical problem. That means very complex problem. Any small disaster can lead to a small change can lead to a big disaster, right? So, but the actually here, the scientists have tried many algorithms, many techniques. Finally, they say that when a simple linear regression model is best suitable for this one. This is what we have to be actually understand a little bit deeper. We are all familiar with the linear regression, a simple equation like a y is equal to mx plus c, right? And then we know that this is actually a straight line, but what we want is a trajectory, right? What we want is a trajectory. So now, but we know that if you can get a data points close enough to each other, even a linear fit also can lead to maybe a trajectory, right? As a curve. Maybe some of you may be teaching computer graphics course. In the computer graphics, we say that how you can draw a curves, right? You can have multiple line segments can lead to a curve, right? But the point is, the point supposed to be close enough, right? The points which you capture the close enough, because today the technology available us to take the points can be very close, so we can get a better linear fit. But the idea is another one here is, suppose in case if I take a sophisticated algorithm, maybe a neural architectures, and may spend a time on that, the neural architectures may be taking that one like a 3 seconds of the time to find this one. Maybe the 3 seconds time may be large enough for a rocket to be going to its orbit, correct? So once it reaches to its orbit, there's no point in finding the trajectory, correct? So normally what will happen is you have to compute the trajectory well before the rocket is going to its space. Then only we know whether the predicted trajectory could be the same way that the rocket is going or not. So the most important is rather than the finding the more sophisticated outcome, maybe it is better to say that when the outcome is supposed to be available with us in the stipulated time. That means when we need the kind of a response, we should get that. It's not that only maybe you can give a better response than that later point of time, which may not be useful, right? Of course, that may not be same always. Sometimes you may have a problems may be appear as a simple, but the solution could be a more complex. That is also be possible. See, the idea is always better to try simple solutions first, so that if at all this simple solution exists, better to go ahead with that rather than going for a more complex solution for this. Now, just look at some of the this is a cartoon which was I took from the kdnuggets.com, where a lot of recent details about the AI and then AI allied areas. They will post it, even including the conferences and the data sets and everything, the kdnuggets.com. Here, there's a kind of a couple went to a dinner, and they want to order their dinner, and the waiter comes and say that one, okay, he comes with a smartphone. He says, smile. Our AI will take a picture of your face and will know exactly what you would like for dinner tonight. So that means the AI agent which sits in this smartphone can able to identify by doing your face recognition and then other aspects. It can able to decide how much they are, how much, how much they are hungry, and what are the quantity that they can take, and it also knows what your interests, what you want to take. Then maybe what you, based on the data, something data like you what you're taking the breakfast, lunch, and everything, right? So it gives the it try to prepare the menu and provide it. But again, system will be, though it is at the end it is a system, not a human being, right? So sometimes it is predicting it, and the predicting may not be always 100% true. Even suppose if you are using the Google Maps to go from destination from one of the point A to point B, sometimes there is a possibility that you may not get the correct result, right? So sometimes you may be seen in the Kerala, one of the person is actually traveling in a car, and the Google Maps actually taken him to a canal, right? Towards the canal. So that's what, in case suppose our prediction is the AI system prediction not good, maybe we may get a food which is actually difficult to even to understand what it is means, right? So that means the AI is being used to make decisions about your life, whether you like it or not. That means irrespective of whether like it or not, today we are using AI heavily, right? So that means that AI has to be in place with us, around us. So this is another cartoon again, taking that there's like a fridge and then there's a stove. They say that again this old couple, they decided to go to a dinner outside because the refrigerator is not speaking to the stove. Because the refrigerator do not speak to stove, that is, there's no communication between these, they failed, because the stove may not be knowing that one what is the kind of a vegetable that you are having in the fridge, or maybe how much quantity that is there, right? The lot of information may be missing. So of course these are the cartoons, but you can see in the reality today we have fuzzy washing machines where you can, based on the dirtiness of the cloths, it can decide how much of the detergent it has to keep, right? So it can decide itself. And of course based on the load of the weight of the cloths, and it can decide that, how much you have to be make the wind and tons and everything. So then the Google self-driving cars, I think many of us knows about this one, and then how the maybe a complex neural networks can able to completely visualize what is happening on the road, including its lanes and everything, and then do the autonomous driving. And this is an interesting thing. That's the edge AI, the way the autonomous vehicles are going on. And then here you can see the data that is generated by each and everything will be enormous. And we need to process the data. We need to process the data in the real time, right? That means on the fly, we need to do real time, we need to do the process the data, and on the fly, you have to do the analytics. That means when if your car is going on, suppose if you are traveling, you're going in this car, and if you want to take a kind of a override is the previous car, then what you have to do, you have to increase the speed and cross this one, right? Maybe during that time, if this car is also, he also actually increases speed, then automatically what happens, it has to be come back and then put into the lane, right? So all these things has to happen. The decision has to be taken place in the when when it is actually processing and getting the result, right? That means like a more on the fly decision has to be taken place. Moreover, once some of the sensors could be like a kind of a traffic cameras, but there may be several other sensors also required you need the information for this. So that means we need to have a kind of a data fusion. That means data comes from the multiple angles, and we need a good amount of research needs to be done on the data fusion to appropriately take the decisions. And the data could be maybe not be in the same format, right? Maybe the drone could be given in a different format than a kind of a AI-driven welding machine, right? And all of us, we know that when you are giving on to apply some machine learning algorithm, the data that which you are having, the data type supposed to be same on which the data was trained, right? Otherwise you may not get a correct results. But in this case here, you can see that each and every, like a smart watch and smart TV and smart city, correct? Each one is having a different kind of a data types and data formats. And as we have seen earlier, that we need to have a data fusion. and the data fusion has to be done on the multiple data types. So what we are doing currently in the deep learning is, okay, you convert into a embedding like a text, and you take another data into like a image, and both in the embeddings you are doing the concatenation, or sometimes you may use maybe a pairwise multiplication, right? So this is the operation we are doing, but because when these two are the vectors, can we say the semantics associated with these two vectors are same? Is it possible to know that the semantics associated with these two different data elements could relate to something, else, or maybe they are different, or maybe they are actually same? Correct? This is like a good amount of research is happening in these kind of aspects. Now let us see how the actually AI is evolved over a period of time, because now we are finding the term generative AI is really actually a game changer in the whole AI evolution. In the beginning, when we started the automation, right, our idea is to make the a business process to run automatically. That means you can create a workflow, and then the task can be specified, and all the tasks can be executed one after another in the sequence, or maybe in the way that you designed, and may do automation, right? That's what we started. Now currently in the AI based systems, we are more interested in the decision making capability, right? So in the AI is mainly for decision making. So now what is the trend is going on? We want to incorporate the decision making capability as the workflow is executing. That is actually a kind of on the fly decision making means. So now suppose you are taking a picture using your smartphone, the faces are already discovered, already recognized, not discovered, is recognized. So how it is able to recognize? Because it was not trained on our faces, but still it is recognizing, right? So that means the AI agent sitting in this one can able to take decision and writing the bounding boxes around the faces, right? That's what the AI based systems. So that means we want to incorporate the analytics as part of the business workflow. That's why we used to call in the industry, in my previous example, we call it as like a embedded analytics. Embedded analytics. Now, just look at what is we started with traditionally we started with the AI in 1960s. Okay? The John McCarthy has coined the term that AI, and the idea is to say that whether the machines are having the capability of thinking, right? The machines have the capability of thinking. This is what we are struggling, right? How we can say they are actually machines can think. But today it may be reality that because the things also started thinking today. Because your smartwatch is able to think, and your smart classroom, maybe smart city, right? Everything, anything can be in the thinking. That means obviously with the IoT, especially with the IoT kind of a extensions or enhancements in the technology, making us the things can start thinking. So now that means that we can actually at least believe that the machines also started thinking, right? But what is the back end of this AI? Is mainly the rule-based systems. If you study the even the AI book, the basic traditional AI books, they are mainly like a rule-based systems. Maybe the rules were actually coded in the form of a predicate logic, a propositional logic, a horn logic, descriptive logic, okay? Or maybe in the logical forms, maybe prologue or Lisp kind of a logical forms. They can able to represent it. But the underlying is a rule-based system. Either you can call it a rule, or you can call it an insight, or you can call it a pattern. But this is like our rules were given to us, and then we are trying to getting this one. Now, if you may be knowing, many of you may be knowing that the expert system, the first expert system is mycin. Okay, that mycin is having thousands of the rules are coded based on the symptoms that is coming. The patient the symptoms, it is able to identify the diagnosis, which kind of a disease, or maybe which is a proning to which kind of alignment, right? So that means there is a huge amount of the rules were coded. The point is the rules are actually given by the domain expert. Rules are given by the domain expert. That means the domain person who is having a huge amount of the knowledge about their experience and giving that rules, and then this AI is actually building those rules to perform what, or maybe to take a decision capability. So now the next is we have a machine learning and pattern recognition. And the machine learning, what we are doing is we are actually having a set of algorithms like a supervised, semi-supervised, correct? Semi-supervised, maybe reinforcement learning, deep learning. So many things we are talking about, like algorithms are there. And then we have a data, normally call it as a historical data. And then we train the model, the algorithm on these models and get a models, and this model is used to predict the patterns, or you can call it as a insights, or you can call it rule. So these may be representation will be different, but they are conveyed different, right? Yeah, I think some Sunil has actually raised a hand. Can you please speak? Someone has raised actually. Am I audible?
నేనే స్నానం చేపించా కూర్చోబెట్టి పాపం ఇక్కడ అంతా తెలుసారా స్కిన్ లేసిపోయి అది ఒక సైడే పడుకుని ఉండి టాయిలెట్ పోస్తే డైపర్ లేకుండా ఒక సైడే పడుకుని ఉండి ఇక్కడ పుండు వచ్చేసిందిరా మళ్ళీ ఇటు సైడ్ కొంచెం వచ్చింది అది కొంచెం తగ్గింది లేను ఇప్పుడు ఇటు సైడ్ కింది పడుకోబెట్టా డైపర్ ఏమంటే
So have you asked any question? I could not get you.
No, sir.
ఇలా
Please continue.
పడుకున్నప్పుడు దానికి ఆనుకున్న కవర్ కి అది ఇంకా స్వెల్లింగ్ అవుతుంది కదా స్కిన్ సెన్సిటివ్ కదా స్కిన్ పైది పోతుంది దాని దెబ్బకి ఏమన్నా యాక్టివ్ నేను ఇంకొక 15 days ఉన్నానంటేనా
Okay, yeah. Maybe some crosstalk. I think somebody busy with some other works.
ఇవాళ నాని బిలువు అంటున్నాడంట మా అమ్మ వెళ్తే కూడా నాని రమ్మని అన్నాడంట అమ్మని పొలం అమ్మేసి
Maybe somebody can unmute him. Sorry,
Okay, someone please remove him from the group, sir.
yeah, someone, because he may be having some other discussion conversation.
Admin, please remove the person from the group.
Yeah, admin is there.
Sorry for the interruption, everyone. We are looking forward for it, sir. Just a moment.
Okay.
You can carry on with the session, sir.
Okay. Thank you.
Thank you.
So now the machine learning, the idea is have a historical data, apply one or more techniques like algorithms or techniques, build a model, and that model is used for discovering patterns, or we can call like insights or rules or maybe knowledge. This is one or other way of representing the knowledge only, right? So now here the outcome is again the same whatever we have seen here in the AI, right? But the thing is, these are actually in the traditional AI, the rules are actually written by the human being or maybe a decision maker, And here in the machine learning, the rules are automatically discovered from the data. So now you can see the
ఎప్పుడు
domain.
అయిపోయింది 4:30కి 4:15కి వెళ్ళిపోయింది.
So the domain expert is having a good knowledge and writing the rules, and then this similar kind of efforts are made for discovering this one. Assuming that one, whatever the knowledge that the domain expert is having may be hidden in this data. Okay? Even when we call about the many of these definitions, we are extracting the hidden patterns. Okay? Now the idea is, what is there in the database? It's like a transactions. Maybe if you just look at an example of a bank, or maybe some kind of a customer related one, maybe these are like a customer spending patterns or maybe customer transactions. So now these transactions, the way that the people have done the transactions, maybe having the knowledge that is taken care by the domain expert, right? Otherwise we cannot able to discover. That means that these transactions are reflecting that kind of a discovering some kind of a knowledge out of it. Otherwise, we cannot say that the rules that are extracted from the data will be useful for us. So that's what the machine learning actually trying to discover the rules automatically. Now there's a data mining. In the data mining, most of the techniques could be similar to what we do in the machine learning, other than the associational mining. But here in the data mining, they are mainly focusing on solving the business problems. Maybe like a fraud detection, or it could be like a kind of a loan maturity analysis, or maybe profitability, the portfolio analysis, or it could be like a symptom early cancer detection, right? So they're trying to solving a business problem. So this is directly applicable to this one. Now, what we have seen, suppose you just look at any algorithm like a decision tree in the machine learning algorithm. The decision tree algorithm can be used on multiple data sets, on multiple domains also, right? But is the same algorithm can be useful for any kind of a problem? Maybe we may be required some kind of a business knowledge to that one, right? So what we do is, in addition to the algorithm, what we consider in the machine learning, we take additional knowledge from the businesses, or maybe mostly from the business terminology, we take as an advantage of that one, and we try to solve the problem. That's what data. Of course, associational mining is like a separate area itself, is for the data mining, where we want to know which kind of the features can we go along with the another set of features, right? The X implies Y kind of things. So then there's the agents and robotics. This is also an area which is coming up. And now you say that like a modern AI is nothing but the agents, right? Or multi-agent systems. These agents are nothing but soft bots, right? Or maybe you can call like a chat bots. So, but robots are nothing but a hard bots. Right? There's a hard bots. So now this chat bot, today you open any kind of a website or any other system, we get a kind of a window saying that may I help you, okay? There's always will be a window. So here an agent is actually responding to our queries, not a human being. So this is nothing but a chatbot, or maybe you can say a software agent which you're looking for. Now, in real world, what is the agent? Actually, agents are nothing but a specialized skills. A person which is having a special skill, we can call it an agent. And then suppose we want to go for a driving license, maybe going for passport, or maybe going for some other work, we usually approach through an agent, okay? We also can do the same work, but an agent can do faster than us because he was actually having a specialized skills, or maybe he may be having a very good amount of knowledge than us in that particular domain. That is a particular specific domain, right? Because he's very good in the domain. So that means the work that what we want to discover the rules using machine learning, we are trying to offloading our work to an agent. So now that agent will do the things. Normally, whenever we call it an agent, that means agent actually looks at the environment, and based on the environment changes, he will take a decision. Okay. So this actually leads to multi-agent systems, because if you require multiple tasks to be carried out, and each task is done by the different node or different agent, could be in a different manner. So maybe multi-agent systems, they can coordinate, multiple agents can coordinate each other and perform a particular task. Maybe if you develop a kind of a soccer kind of a game, and then many people may be trying to hitting the ball, and then you have to find out the kind of a the at what rate that the player is running, and also at what rate the other players are running, and at what speed the ball is rolling. So you need to take several conditions in place, right? In place, and then take maybe the coordinate among these things, and then take a decision whether how speed that you have to be hit the ball, right? So, and even this multi-agent systems today, many of the times it's not possible for us to do the things, and then maybe we may ask that taking help of agents, correct? So then this is called autonomous systems. This is actually a bigger game changer was happening in the autonomous systems, where it can be able to learn themselves, like they having the capability of self-learning or self-configurable. Self-learning or self-configurable. So these autonomous systems look at the environment, and if required, they can change. Like as you have seen with the Google driverless cars, right? And today, suppose you have a cloud service provider having thousands of the nodes in this one, and it is like impossible a human being to identify a particular node is dead or active, right? So then suppose if there's any failure has happened in a node, and if when it was rectified or failure happened, how it can able to hand over the jobs done by that particular node to the other nodes, and when this become live again, how to take over those jobs, right? How much handshaking has to be happen among its active nodes, right? And we have actually done one of the project, which is a very interesting project in this area from the software testing. So here, the one of the mobile service provider, he wants to develop a testing where the software code cannot be given to anybody else except the developer. Nobody else knows that one, because the competition, they don't want to reveal the kind of a code that they develop it. So then what happens is, suppose if at all you want to write a develop test cases, you have to see the code. Okay? Without the code, you cannot able to test it. Without testing, you cannot deploy it. Okay? Because once the software is developed, and then unless it's thoroughly tested, we cannot deploy it. Now here is like a locked manner, okay? Because if you don't release the code, they cannot test it. Test cases cannot be developed it, and unless testing is not done, they cannot be deployed. So then what we developed is, we have considered like a long arm project. The name which again long arm project, which can actually remotely can look at the screen of the mobile phones, and then try to look at the kind of suppose if you have a kind of a app, and you click this one, it may be going to the another screen, and maybe they scroll up, scroll down, or maybe some other buttons will come, and then some kind of boxes will come, right? So it will this agent will try to learn what is happening here by interacting with the screen, and then write the test cases. That means, if at all if you want to write a test cases, we should know the functionality of the code. That means the code is required, or maybe functionality of the code required, right? Now, what we are doing is this agent actually discover the functions. The functionality of the code is discovered, and then accordingly writing the test cases. Now you can see, that means not only that we are actually modeling the one, but we are trying to take the behavior of the functionality also. That is like a functionality discovered, correct? So then only we can develop such kind of autonomous systems. Then the next trending topic is like a deep learning. Currently, if you ask any of our students to do the project, 90% of the people, they say that they want to work in the deep learning project, okay? So now why they say that? Because we already know AI, we know the machine learning, and then the autonomous systems, and then why suddenly the deep learning is coming to place? Now you can see, whatever required for a machine learning, the basic thing that is required is the features, right? But if you take any algorithm like a decision tree also, or Navy Bayes, or support vector missions, or neural network, you take any of the machine learning algorithm, the input is the feature data. That means, first of all, we should know the features. Suppose if the data is in the structured data, and I can say some of the columns can consider as a features, can serve as a features, right? But what happens if I have a text data? If I have a text data, then the text data I need to convert into a features, right? Maybe I may use bag of words, or maybe n-grams, maybe use TF-IDF, or could be key phrases, or maybe name entity extractions, name entities, everything, right? So that means I have to somehow I have to convert the text data into identify the features, and then apply my machine learning algorithm. If it's like an image, what we need to do is we need to extract the color features, or maybe texture features, rotation features, scaling features. Maybe many of the features we need to extract it, and then we need to apply machine learning algorithm. Now here is the catch. Suppose if at all, if we don't, in image processing, some of you can ask the researchers in image processing, they used to come out with a new feature descriptors, because these existing feature descriptors may not be efficient enough to recognize an object. So they are trying to develop a new feature object, new feature descriptors. Why it is required? Because maybe these existing feature descriptors may not be learn the information completely, right? That means may not have enough knowledge to do that. So that's why we actually come out with a new feature descriptors. Now, this process, this feature engineering in the machine learning is a biggest task. The most of the considerable amount of time the machine learning expert has to spend time on identifying the features. Once you identify features, then that is only to find out which algorithm is more suitable and apply on that, right? So feature engineering is taking a huge amount of the time. Is it possible to make my algorithm itself, take my algorithm and take that, it itself will take the features. It can able to identify features. So that means, can we make the feature engineering is part of the algorithm itself? That's what the deep learning is coming to place. Right? The feature engineering is a implicit of the deep learning algorithms. That means you don't require to extract any features. You just give your image to the deep learning algorithm, it will try to identify what object it is. Right? Maybe some of you may be knowing the CNN, convolutional neural networks, or maybe the advancements of the CNN architectures. You just give the input as an image, and it can able to give the object which is actually present in that. Okay. So that means the feature engineering is actually part of it. So what is the advantage of this one? First, you can see what is the why we cannot able to do earlier. The feature engineering, if at all, if you want to identify the correct features, you require a huge amount of the data, because you have to perform a huge amount of the corpus of the, you need to perform that one. So then only you can identify the actual features, right? If you take a document, you have thousands of the words. Is it possible to have a bag of words for that? Very, very difficult, right? So now that means you have to see that the features, the relevant features that require to identify the objects, it has to be extracted. So now we can see in the traditional AI, the rules are written by the human being, and in the machine learning, the rules are discovered automatically from the data, but the feature engineering is still manual, like a handcrafted, right? Somebody has to do that feature engineering. But in the deep learning, the feature learning is also happening automatically. That the feature engineering is also happening automatically. Okay. And another side is the computations. Because when you talk about a huge amount of the data, obviously the computations are heavy, okay? Because it requires a large amount of processing. Is it possible to make it faster? Normally, if you have a numerical data, the computations will be faster than the text data or maybe pixel data, okay? So is there any possibility to say that the data can be represent the data into a good form so that the computations will be faster? So now what people have started is to convert the data into vectors. Like you take a word, say word to vector, right? Or maybe sentence to vector, maybe a paragraph to vector, or maybe document to vector, image to vector, audio to vector, video to vector. So that means everything they are converting into vector that normally we call like embeddings. Right? So that means all the data which we have, we are converting into the embeddings, and then vector computations are faster, so you can able to do the huge amount of the data you can process in a less amount of time. So this is nothing but the representing the data, right? So the representation learning and future engineering is both are actually part of the deep learning algorithms, so that we can able to process huge amount of the data in less amount of time. At the same time, we don't require to identify the features. The features can be automatically extracted so that no information will be missed out. The required information, relevant information may not be missed out from not identifying a feature correctly. Right? So that's what the deep learning is doing it. Then there's an area called data science. That is again another new jargon which was coming up. This one, the data science actually started with the addressing the challenges of the big data. As we know, the big data characteristics are like a volume, velocity, variety, viscosity, value, veracity. Correct? There's so many V's were there, but of course, at least you consider the top 3 V's like a volume, velocity, and variety. Right? That means data is not only structured data, we are going to the unstructured data and semi-structured data also. And we want to compute the computation will be more faster and handling a huge amount of the data that's representing the volume. Correct? So mainly to address this big data challenges, then the data science actually arrived. And the data science, what it actually says is, you can apply any technique, whatever that you want, you apply the technique, which are you're familiar, even including a simple Excel sheet or could be a advanced deep learning algorithms you can consider. But it says, whatever that you get the output, whatever that you are getting the rules or patterns, they should be provided a added business value. They should be a value to the business. Unless if you say, I have come out with 100 patterns and none of the pattern is not useful to implement it, there's no point, okay? Suppose somebody can say, okay, you can recruit 15 people of this skill set in the next 20 days and your revenue will be increased by 30%. This is very good. 30% revenue increase is very good for a company. Of course, they are also taking care of all the 15 people salaries also. But is it possible to recruit this skill set of the people in the next 15 days? If this is not feasible, then there's no point of saying that you can implement that rule. So that's what the data science says. What are the mechanisms that you want to use? But at the end, you have to show some kind of a business benefit out of it. That's why the data science keeps a rider on the outcome of this analysis. So that's what the data science talks about it. Then there's a called a quantum inspired computing, because today people are moving into the quantum world, right? So earlier, whenever we talk about a new area, people have started doing research in that area. Like if you say, if I have a parallel algorithms are there, now all machine learning algorithms are converted into parallel algorithms. Now when the MapReduce came, so all the machine learning algorithms are converted into the MapReduce framework. Similarly now, because the quantum computing, the people have started working in the quantum machine learning. Suppose you ask us currently who are doing research in this machine learning area, they say that quantum machine learning is one of the area that is coming up. It actually talks about the quantum principles like entanglement, superpositioning, quantum tunneling. So all these principles that it is used and then use that can be modeled as a part of an algorithm. Okay? That's a quantum inspired computing. So that means instead of representing the data or the representing data in 2 states like a binary states, now we are representing in the multiple states, more than one state that is possible. That's what we are calling like a qubits. Okay? The data is represented, or the algorithms are represented in the form of multiple states, the qubits. But here the outcome is same, but because suppose you are going for the sentiment analysis, you can say sentiment is positive or negative or neutral. Right? This is what the outcome. But is it possible to have only a single model to do that? But what usually earlier we used to do, the historical data, take historical data and try to look at multiple algorithms check some kind of a confusion matrix, or maybe do the accuracy, precision, recall, F score and everything. And finally, you choose one model which is very good for that, and that model you are deploying it, right? But now the data is enormously generating, and the data is evolving. And when data is evolving, the data kind of the kind of a nature of the data is also be evolving, right? The different kind of new data sets are generating. Is it possible to say that a single model is useful for developing for prediction? That may not be, because today particularly in the IoT sensors data, you are getting data is getting continuously, right? Data is getting continuously. So when the data is coming continuously, is it possible to say that, no, okay, let me see this data and then apply some algorithm? Or can I see this data kind of thing and see algorithm? It is very difficult, right? So is there any possibility to see that, can I adopt the data itself can intelligent enough to check which algorithm is suitable for me? That means I have a multiple machine learning models, right? Machine learning models are available, and the models are intelligent enough to say that one can see this data which is passing through me. Can I predict something from this one? I am suitable for this data or not? Suppose if it is good, then it will go and predict it. Otherwise, it will leave it to the other models, right? That means at any point of time, you have a multiple choices in your hand, but choose any one of that and then go about it. Right? That's what the kind of a quantum entanglement is talking about. It. Quantum entanglement, quantum tunneling, or maybe superpositioning. All these are the quantum principles. They are incorporating as part of the algorithms. Then there's a term called nature-inspired computing. And many of us familiar with using this evolutionary computing techniques like genetic algorithms, so particle sperm optimization, anti-colony optimization, right? There are many of the algorithms currently, the shipyard algorithm. So they are actually evolutionary algorithms which people are using as part of many of their problems, handling the problems. What is happening here? That means we are actually adopting some of the concepts from the nature. Suppose you can see in the genes, you have a mutation, slicing, you have a kind of a crossover. Correct? So those are operations you can take into that one into algorithm, we call it genetic algorithms. Right? Crossover, mutation, things. Same thing like anti-colony optimization. You can see the behavior, understand the behavior of the ants and model that behavior into the part of the algorithm. The shipyard algorithm, usually what happens, one ship will take as a lead and all other ships follow, okay? Suppose if you want that kind of a nature, you can have a shipyard algorithm. So today, you can see most of the algorithms which are generated, which are coming out one way or other related to some of the behavior, right? The nature behavior. So essentially, what nature-inspired computing is doing is understanding the behavior in the nature and model them as part of the algorithm. That's what actually is striking the nature-inspired computing. Then the generative AI is taking place currently, right? So in the generative AI, what we are saying is not only you can able to model things and then predict more accurately, taking decisions as effectively as possible, but it says that I can generate also. Right? It is generating. Either you can say generating a code or generating the text. So you give a kind of a text and it will summarize it, right? And if you give a prompt, say that can you refine the statement, it will try to refining it. Suppose if you ask some query, it will try to making it. Today, they actually added the search engine also as part of the ChatGPT, right? So it is doing both search and inferencing. So that means it already learned something and is able to generate it. And sometime back, I actually seen, I'm trying to find some of the research paper to quote some of the statements, which I do not know exactly whether the statement which I made is actually done by somebody else or not. So I actually want to cite that one. So I have given in the ChatGPT, it is actually given a very beautiful research paper to me. Of course, research details, right? The paper details. But I got a doubt and checked it whether this paper is really published in that particular journal or not. When I go and see that one in that particular issue or in the volume, that paper doesn't exist. That means the generative AI is also generated a citation. So now people are actually intelligent enough, are smart and not smart enough to write whatever they want from the ChatGPT kind of applications. So ideally, the generative AI is actually generating the data, correct? Which was actually from the model and which is actually trained by another data set of data, right? So that is the actually interesting feature of this generative AI. Now, whatever that we do, because the huge amount of the data is generating every day or every second, and we are living in the data-driven world, and data sense is more important than anything else. It's not that on what technique that you are using. Either use a simple AI technique or you can use a advanced language models that you want to use it. But at the end, can you sense the data? That is more important. It's not that I have a huge amount of the data, because the organizations today have a huge amount of the data. It's not that the amount of the data, but they can sense the data or not. That means, suppose somebody is doing a loan transaction, right, or maybe a credit card payment transaction, is it possible to find out whether this credit card transaction may go to a fraud, may become a fraud? Maybe some of the cancer patient data, analyze it, and maybe saying that maybe next 3 months it may go to second stage. That means you are understanding it. That means you are sensing the data, correct? Of course, for sensing, you require a huge amount of the techniques and algorithms and everything that may be required. That's okay. But you are able to sense the data, what is with you, right? So the data sensing is more important than the what kind of algorithm that you are using it. Of course, algorithms will try to provide good insights once, but it is up to you that whether you want to choose a simple Excel sheet or you may be using an advanced generative AI techniques. So overall, what is the point is, because as a humans, we have the capability of thinking or maybe having a cognitive reasoning. That's what our specialty, right? The humans are good at cognitive skills. Now we want to incorporate that cognitive reasoning into the mission as much as possible. Okay, so that's why when we started, we say that the machines are started thinking. Now that maybe the thing that what we are saying is machines can think as human as possible. So that means we are introducing cognitive reasoning to the maximum that can be possible into the machines, so that the machines also can serve as a, or maybe treat as a human. So just to recap, what is that we discussed till now? We have a in the rule-based AI, that is traditional AI. The rules are designed by the human being, or we can say it's like hand-designed rules. Whereas in the classical machine learning, the rules are actually learned automatically from the data, but whereas the feature engineering part is the handcrafted, right? That means like a hand-designed feature. The feature engineering part is mostly manual. In the representation learning or in the deep learning area, not only we are learning the decisions or learning the rules, we are also learning the features. That means you are automatically extracting the features. If you look at the convolutional neural network, except the last layer, all the previous layers you are using to identify the features. Because we have the base, we have the pixels information, and doing the convolution, ReLU, maybe pooling layer, many of the layers you are using, or maybe another set of layers you are using it. But what is the output of those layers, except the last layer? The features only. Because you are trying to identify the features that are relevant for the given training data to determine the objects. And the final layer, okay, the final layer is only a kind of a neural network layer, or we can say fully connected layer, right? Based on the input into the fully connected the features, and it trying to prediction. So, but the rest of the previous, all the layers are actually trying to get the proper features. That's what the deep learning is actually today talking about, right? You can use all the algorithms to find learn the features automatically, or maybe extract the features that are relevant for to solve the problem. So now here actually a kind of again, there's a small catch here. If at all, if you want to learn the features automatically, you require the huge amount of the data. Suppose I am doing a kind of a a sentiment analysis in on the banking sector or a banking product. Suppose maybe banking has launched a new product, maybe new scheme they started, and they want to identify the sentiment. So you have the huge amount of the data, right? You actually tried on this one and maybe made this one. Now you develop a model, you had a deep learning model and everything. Now suppose if I ask, now you already had experience in the doing banking. Now can you do the same thing for the insurance claims? Yes, we can do it, but maybe we need to start from scratch. So I have the data, I need to start from the scratch and building this one. But you can see while doing this exercise, I spent a huge amount of the time on this one and I learned a lot. That lot of knowledge was learned by me. Now, is it possible, rather than starting from the scratch, again to start from the first, is it possible to transfer whatever I learned earlier to here? That's what we are coming to transfer learning, right? We usually call it a transfer learning thing. So now with the transfer learning, what is happening now? Whatever that I have actually learned here, I am using that one. Maybe I can say how it is possible, because in the banking reviews on the banking product, mostly maybe on the English language, correct? Suppose this insurance claims, they also may be in the English language. In case if I trained something data on English comments, maybe it may be useful for me so that I do not have to require those things to do again. Maybe I can say, maybe I can develop a corpus, or maybe learn a model on the English corpus, and I create a pre-trained model. Right? I develop a pre-trained model, and that pre-trained model is used. If suppose if I want to use a banking sector, I can use the banking data to be a little bit train that one. That was, we can call it as a fine tuning, right? I can do the pre-trained, take the pre-trained model and fine tune them for doing a specific task. And similarly, if I want for insurance, I take the same pre-trained model, but fine tune again these things, and I can do the insurance sector. That means what we are doing is, suppose in this, like a bird, some of you may be familiar with the bird. But is a transformer, right? So it actually trained on a English corpus. So they have a pre-trained model and fine-tuning. So these two together having the concept called transformers. Called the transformers. So the pre-trained. Now, another thing is here is, because we are not talking about the small data sets. We are talking the huge amount of data sets, that is like billions of the documents. So when you have such kind of a huge amount of corpus, it is not possible to annotate or maybe to give a label to that one. Okay? It is very difficult to get a label data to train that one. Maybe we may go for a semi-supervised learning. Right? We may have to go for a semi-supervised learning. Or sometimes people are also calling like a zero-shot learning, few-shot learning, okay? Or one-shot learning. Okay? That means the number of samples are very less, and but I want to train that one. So this is these are the concepts actually built up to have a transformer, like a pre-trained model. Take pre-trained models, fine-tune them for the specific task, and if required, you can use some self-supervised techniques to train them. So this is actually building a transformers. So now, what is actually happening at the back end? What do you mean by pre-trained model? Okay. So here is things. Now I'm having the features, I'm learning the features, right? But whenever you want to handle the task, what is at the end we are required? Well, as seen in an example, we have seen that there's multiple layers will be there, and finally you have a neural network layer, and you're getting the prediction, right? So that means all these layers are helping out to extract the features, and these features you are giving to the neural network for predicting. So now, if I take another one, this one, what I'm doing, I'm taking this kind of features, correct? Some other model I'm using, I take features, and again I'm giving to some kind of a network for prediction. Now, the deep learning, what is actually doing is there in the particular transformer technology, is it possible to develop, because this is the kind of a feature, and this is the kind of another feature, set of features, is it possible to generate a abstract features? Correct? So that means, can I generate a abstract feature so that the actual features can be instantiated for a particular task? Correct? So that's what the things are coming as can we have a learned abstract features? That means rather than discovering the features, is it possible to discover or maybe learn the abstract features? So if I take the abstract feature, I can use for different purposes, correct? And most of the times we see when you define a class, but why not we define object directly? But we are defining class, correct? In object-oriented programming. Why will do class? Because I can instantiate multiple objects out of it. Maybe it is some kind of changes. Maybe I do some kind of additional properties or inheritance, something I will use it to add it. But the core is that when I have a class, like an abstract class is abstract, right? And then I'm creating an object, the object is real. So that means here, in the similar way, here also we are doing, instead of learning features, I'm learning the abstract features. And those abstract features can serve as a transformer. That's what the pre-trained model means, right? The pre-trained model. That will be fine-tuned for a specific task. Even the BUT is also there, is a generic one, an English corpus, but they actually trained on the name entity extraction, summarization, parts of speech. So there are different variety of NLP tasks can be handled using BUT. Of course, they have their own limitations, but this is what people are working into this direction. So this is actually completely encompassing the complete data science journey. So I'll give a pause here. Any questions here? Any questions? No?
Dear participants, if you have any questions, you may please ask, sir.
Yeah, either you can unmute or you can keep in the chat box, because I cannot see chat box, but someone can read in the chat box. So if you unmute, I can answer directly. Otherwise, I can read it later.
You can raise your hand or even put a text on the chat box or ask.
So anytime you can ask me, you can stop me. I will answer it. Okay, there is one chat question was there. Let me check. No, it's a general message only. No, feature extraction means what? Okay, it's good. Good question. See, now what happens is, feature extraction means, suppose you have a structured data. That means we are actually defined columns or attributes or dimensions, we call, right? So these are nothing but these are called maybe a column, or can be an attribute, or dimension, or a feature. All are same only. In different contexts, we use different terms, but they are the same only. This is nothing but a feature. So that means an attribute can serve as a feature. Sometimes what will happen, the 2-3 attributes can also serve as a like combined feature, one single feature. We can actually combine that one, make it a feature. Okay. When we have thousands of the features, and maybe our model may not be helpful to high dimensionality, we use some kind of a PCA, and many of you may be knowing principal component analysis, support vector decomposition. These are useful to compress these features. That means, suppose you have a n number of features, you can compress to p number of features. That means p is where p is less than n. Here in the PCA, there may be one-to-one correspondence. Suppose you take n features, like I say, assume that there are 10 features are there, you are taking the 3 as the reduced features. There may be one-to-one correspondence, but these all 10 are actually some way it was actually combined and then formed as a tree. Combined some combinations. That's what called principal component analysis, right? Maybe like if I have a two-dimensional one, a two-dimensional data, right? I can put in a single dimension to do the projection, right? I can do the projection. Similar 3 to 2 like that. Now, in the text data, this is very clear. These are another features that we need to identify, right? We need to extract those features from the data. But the problem comes when this data is unstructured. Suppose you have a text. This is like a text was there. A lot of text words are there. Then, suppose for any machine algorithm, you require the data in the form of a features like this. You have the columns over there like this. Each record will be there. These are the features. Now, these features are not available directly from this data, right? We cannot make it. Then we need to use different techniques that called a feature extraction techniques. So we have the features, but we need to extract the features. For the example, you can say each word could be a feature. Each word can be a feature, right? If the feature exists in this document, that means all words. So if word exists, I can write 1. If the word doesn't exist, I can 0, right? So that means now what I did is I converted this entire document into some kind of a columns which represent the features, and I'm adding rows for each document. All unique words will become the features here. But in the text document, how many number of features will be there? How many number of words will be there? Unique words? So many, right? Thousands of the words will be, unique words will be there. If the 1000 is a very large, then what we do? We try to use some kind of mechanisms like a stemming, stopword removal. All those approaches we do, and we try to minimize these features, relevant features. So that is the extraction of the features. If it is the image, what we do? We try to identify the color features. What are the colors are there, and suppose you assume that when there's each pixel information was there, and in the RGB, right? So now what do you do for each and values are there here, right? The color feature, that means you are extracting the color features, the texture features. Like that, some or other mechanism you are applying on this data and getting the features. That's called a feature extraction. Is this clear? Amurtavalli. Yeah. Is this okay? Okay. Very good. Thank you. So now, let us see another dimension. Because we are saying so many times we are applying algorithms, right? For what purpose? We want to solve the problems. How? We want to train the system to solve the problem so that any new problem given, it will try to solve based on the learning. First of all, we need to understand what is a learning means, right? What is a learning means? If we understand what is the objective, then you can understand any algorithm easily. Because the mechanism may be different, right? The mechanism may be different, but the objective is same. Suppose if I know, if I am here, standing here, and I want to reach here, right? If I know the target that I want to reach here, I can do either I can go walk here, or maybe make a big jump to reach here. Maybe if I am become old, what I will do, I will take a walk sometime, and take a step, and then take a walk some more time and step, and then walk some more time step. Some mechanism I will use it, right? Maybe some angle may go like this. There will be many varieties. So the first of all, the important thing is what is a main objective of learning. So this can be actually thought from the 3 different dimensions. One is of course, dimension not to confuse here. There will be 3 different directions. So one is the data space point of view, another the model selection, and the control plane. So the main objective of any learning is take any data point. Can you distinguish or distinguishable from all other objects? If at all, if you can do that, that means you learned it. Your learning is completed. How we can say? See now, if you say, suppose, assume that one is a sentiment analysis, all the posts belongs to this one are like a positive, all these posts are belongs to negative. Okay. Now you got a new post. Suppose what is it is somehow some mechanism I use to get a kind of a curve like this. And I can say below the curve, if the point is there, I can say negative sentiment. If it's above the curve, I can say it is a positive sentiment. Correct? That means I am able to know it, what it means. I am not saying the distinguishable means is like a altogether new object. No. I say that what it means. That's what we call it data sensing, right? So what it means. If you can understand that, that is sufficient. So here, because of this model is giving me like this, though I can say it is negative sentiment. Correct? Now, is it possible always to do that? Just take an example. Suppose if instead of a curve, I can go up a line also. Correct? I draw a line, and I can say below the line, if a post is there, I can say a kind of a negative sentiment. If it is above the line, I can say positive sentiment. Okay, here I may use a linear function to separate it, or here I can use a curvilinear function to separating it. Right? That will be based on some kind of historical data. I am trying to bring it. Let us see a simple example, which I usually give the example is, suppose if I am standing on a road, there are many vehicles are going on this road, different types of the vehicles going on. Is it possible for us to see all the vehicles on the road? It may not be always, right? We cannot see always all the vehicles. Suppose if I say there is a big bus was standing here, I may not be see there is a scooter before this one, right? I cannot see that vehicle, because this object is actually hiding me from that. So now suppose I have a building next to the adjacent to the road, and I go top of the building, and I try to see the vehicles. Can I see all the vehicles? Mostly yes, correct. I can see all the vehicles. But what is making difference here? Earlier, I am only part of the two-dimensional. I am part of the two-dimensional. Now, what I did is I am looking for the third dimension. If not third dimension, I will go to fourth dimension. I am going to go to fifth dimension. I go to nth dimension. Till I will be able to identify each and every object. Correct? So that's what we see in the support vector machines. We go for hyperdimensions. Why we go for hyperdimensions? Because we want to look at that one. And you can see some of the data sets which are very overlap data sets. It's very difficult to classify a point whether it belongs to this class or this class, right? And maybe a good example is the iris data set. All of you may be familiar with this data set, right? Iris data set. In the iris data set, this is like a flower data set having data about the pertaining to 3 flowers, and each flower data is having like 50 samples, right? Having 50 samples. That means total 150 samples, and having 4 fields: petal length, petal width, sepal length, sepal width. I think all of you might be familiar who are working in this machine learning area. They know familiar with this iris data set. But in this data set, out of 150 samples, see, all traditional algorithms fail to classify all the samples in there are 3 classes, right? All the samples in the second and third classes. First class, at least they can able to do it, but second, third, they are. Why? Because you can see you want to differentiate a particular object. How we can differentiate? Our base is same, right? The features. So for a sample, for these 4 values, we are not able to, based on these 4 values, we are not able to distinguish whether that belongs to class 2 or class 3. That's why even today the iris data set is more famous, because whenever somebody comes to a new algorithm, they will try to implement on the iris data set. Of course, with the deep learning advanced models, you can do easily distinguish, but traditional models like a decision tree, random forest, you may not able to do that one. Because these 4 values, you can see based on these values, they are not able to determine which object it belongs to. Okay, so that's what actually we need to do here. So in case if I am not able to represent, can able to distinguish with a line, I can go to curve or with a quadratic model or cubic model. So that means I can increase the models, complexity of the models. I can choose a different kind of a models. Like as I mentioned here, decision tree, like a random forest, you can try. That is random forest is like ensemble, right? Maybe you can use a deep learning and neural network algorithm, or you can use a deep learning algorithm, or you can use a high-end algorithms. And then now suppose if I want to draw a line here to separate this one, maybe there are many possibilities, not only one line, right? There are many possibilities to separate this one. Which one is correct? So for that, what I'm doing is I'm trying to find the maybe a kind of a mean squared error, right? I'm trying to use the reducing the mean squared error. Normally we also call like a loss, perception loss. In the most of the deep learning algorithms, we are using the cross entropy loss, right? So that means we are trying to use some or other methods for error analysis. Error or loss, we use either term error or we use the term loss for doing this one. So that is nothing but a control plane. So you are controlling that algorithm one. So we have to see this from the three different directions. We can see that one to classify this particular object. If at all, if we are able to identify that, that means we actually learn this one. So all the algorithms are trying to do this one, right? If you take a neural network algorithm, what you will do? In the back propagation, you're trying to adjust the weights. Why you want to try? How you are trying to adjusting the weights? Because there is a predicted value and the actual value, the difference was there. You're trying to minimizing this one. Right? So this is what actually gives the learning. So all our faculty members are very active. So, things. So this is actually object of the learning. If you can know this one, then we can able to clear about most of the aspects. So what exactly we are doing is we are actually in the original space. The data is in the original space. We are connecting to the future map or future space so that we can able to distinguish the objects. Okay. So you can see the different kind of models are available. Some of the models are the generative models. Some of them are the discriminative models. And you can see a variety of the models are the coming into the deep models and CNN models, everything. And today we are having a kind of a generative AI, right? Generative models. So in the generative models, actually it looks at the data and try to get some kind of a reasoning or maybe kind of patterns out of it. Whereas the discriminative models are mostly focusing on finding a kind of a plane or maybe kind of boundary that separates the different classes. And this is like a generative and a discriminative models. So of course we have a different kind of a learning paradigms for there. Supervised, semi-unsupervised, reinforcement learning, self-organization, the things. You may be learning in the course of this complete all these sessions in the one. And the deep learning is the mostly based on the representation learning and feature engineering. That's part of it. But it can be either supervised or semi-supervised or unsupervised or anything is possible. So now let me skip a few of the things. Now we can see the variety of the data is generated. The earlier we are actually focusing on the application generated data. With the social sites, we have user data. With IoT, we have started with the machine generated data, right? That means we need to handle multiple aspects of it. So now there are a lot of work is happening here. So we have a deep neural networks, and then we go for the RNNs, recurrent neural networks, and then we have a LSTM, right? Long short-term memory kind of things which are happening, the advancements of in the neural networks. So though in the classroom we talk about very smaller, here we have a typical DNN. You can see for the kind of a many of the things like you can see people are actually using different kind of a model settings. So now we can see whatever we understand till now is we have a pre-trained models kind of things like a transformer architecture, pre-trained model fine-tuning. And we have a self-supervised learning capabilities because the training data may not be labeled data in the one. And we have a computing power. Today we have a huge amount of computing power, right? That all leads to a perfect storm towards this generative AI. So that's why the generative AI is powered by the large language models. They provide a transformative possibilities across multiple disciplines, which could be like a healthcare, or it could be like a retail industry, or finance industry, correct? Or in the kind of a customer services. In each and every area, it is actually entering the generative AI. Even today, if you want to have a poetry, you can ask that one, okay, give some kind of a kind of a prompts, you can get a poetry out of the generative AI, correct? From ChatGPT. So the ultimate idea is whatever that you want to taking the patterns, right? Usually the patterns are maybe rules, whatever things are, we are making them actionable. Actionable means that we can able to implement it and get an advantage out of it, right? So there are so much of the patterns are evolving, but what we are language models do is making inactionable data to actionable. That means we have a huge amount of the data, but what we are making it is more than the actionable things. That's what the language models actually does. So what is we need of the hour is that we need to embed the business process, embed the analytics into the business process. All the AI is supposed to be part of the business process, right? That's what the embedded analytics we are seeing. Now we are looking for a more on the proactive things. Earlier we are actually taking the historical data and develop patterns and check that whether this is a fraud or not when a transaction happened. But today we want to avoid that pattern, right? Now you want to detect the thing whether it is likely to be spam or not. Then we want to say that right time we need to give the decision rather than the real time. Of course, right time may involve real time, but most exactly that when I need when I'm required the decision, the system able to provide it. Right? And then of course we are having a distributed parallel programming computing things for there, because when you have a huge amount of the data, you cannot say that I will go for a simple sequential manner, right? You may be required a distributed parallel computing, and particularly with respect to the edge computing, you can see somewhat you want to distribute the computing process between the edge device also, right? Either you want to go to edge, or you want to go to the fog node, or to the cloud node. So from data perspective, we have to look at the identify the data is for the social data or stream data, the sequence involved, or maybe data is unbalanced or unavailability. So many of the things were there. And from the technology perspective, you can see there's IoT, then the image and video analytics, including the big data analytics, data fusion, the social signal processing. There are many of the perspective that we can see the trends in AI. And algorithm perspective, we have many of the actions here. Of course, we are taking the transfer learning, deep learning kind of things. There's active learning is another approach. We are doing it like reinforcement learning. Many of the algorithms are tried in this manner. So you can see the trends which are going like a purposeful AI and responsible AI and explainable AI. Okay? There's so many new areas are coming. And I'm actually working with one of the industry and the conversational AI platform, particularly the multimodal conversational AI platforms. So that's what this you can see. AI will recognize us even if we don't recognize it. That because somebody says that I don't know AI, but AI will actually with him only always. Even with the simple smartphone itself is having a lot of AI features, right? So you can see that's what the how the ChatGPT and everything was making different kind of a problems it is solving. Then there's a variety of transformers developed, large language model developed nowadays. Of course, this is also become slightly old one, but you can see now Llama is a popular LLM nowadays. So this is how it is happened, like a GPT and everything. Actually, this word to vector, right? People are started the embeddings. The fast text is actually this is given by the Facebook. Fast text. And the globe and everything. This but was started. But is having different varieties of it. Okay. So let me stop here. So maybe some of the good things as like you have the lot of applications for there. Maybe some of you good to solve. Maybe using LLMs if you want it, like I say, malware analysis, content creation. You can see different streams. Right? These are things. Even visual query and answering also, these are the things that you can use it. Some of the like chat GPT, where they are using the lot of reinforcement learning, because you can see you give some kind of a feedback, right? You are giving that one and you say that whether you get a good response or not, you want to repeat it, right? So with that, you are actually the chat GPT can learn from that feedback. This is a multimodal language models. Right? This is a PALM-E, that is another multimodal language model. This is a visual query language model, because a lot of LLMs and changes were there. We also use the LLMs in the kind of a software testing, particularly to find the software clones or maybe bug testing kind of thing. So these are the works which we have done in that NIT Warangal. And this is clone detection. And then we see automatic seed generation for the LLM fuzzing, because people are now started working with the fuzzers, right? This LLS fuzz, and then the multiple variations of it, we develop it, prompting. Okay. So this is the kind of. So I'll stop here. If you have any few questions, I can take. I don't know what you may be expected, maybe different, and then I may be in this introductory session. Any questions?
Dear participants, if you have any questions, you may please ask.
Maybe it's already late for them, 8 o'clock. So maybe if you don't have any questions, I'm very thankful for the patiently listening.
Hello, sir. Good evening, sir.
Sir,
Yeah, please.
Can you give us some direction towards like how I can use these LLMs like in real application if I want to work on something, like how I can start or use it for some application?
Yeah, we need to think in two different directions. One is don't touch upon the LLM and only take the benefit out of the LLM. Right? Suppose you
Yeah.
want to do
Yeah, that is what I was asking.
suppose you want to say, you want to summarize the text. Right? So
Yeah.
of course, many of the models are already available to summarize the text. Similarly, you can also summarize the text using to the LLM. You can give the chat GPT, it will summarize you and give it. Now you give a legal document, legal text, and ask the LLM to generate a summarization. But the summarization may not be effective as much as you are expecting, right? Because a lot of legal interpretations, they are very entirely different.
Yeah.
Already tried is okay. Already tried, it may be done.
Yeah, ChatGPT we have used already, but anything else like
You can use
using
it,
the APIs, right? Nowadays we are getting this APIs.
Yeah, you can use it. What I'm saying is, but the answers always can you know if they're correct? But all you want to refine this one, that your model can be added. So then what people have started with is, like they can use a term called a transformer, correct? So then now they started like adapter. That means this adapter is specific to your legal domain. See,
Okay.
ChatGPT is a generic one,
Yes.
right? But you are using it, it is giving some answer.
Mm.
In case if you want to able to fine tune the parameters with respect to your legal domain data, it is much better. You will get a better output.
Yes, yes.
Now, suppose you ask a kind of a query, and then your enterprise is having data on the data is there on the structured data, and some of the data is in unstructured form. Okay? Suppose you store some data in the Elasticsearch kind of environment, some of the like in the Oracle databases. Now you want to retrieve it. What you need to do, you have to write multiple SQL statements, multiple knowledge graphs, you have to generate it. So much things have to be done, correct? So now you instead of that, you try to provide some kind of meta information to the LLM, it will be given better result.
Yes.
Okay? So in that way, people are using for like I given a lot of like malware analysis. Even we are using for fuzzing. Correct? In software testing, fuzzing we are using it. Now autonomous vehicle drone, we are using that one. So that means we are using LLM as a tool, but peripheral we are developing it. Our research is more focused on the mechanisms in improving the performance of LLM.
Yes, sir.
The second aspect is maybe within the LLM itself, maybe you can able to add it. Of course, we don't have that much of a compression power like Google is having, right? But because I'm also with like a client, so we have we try to add some kind of a layers in the LLM itself, so that we can get a better address the better problems. Like machine translation was there. In the machine translation, you take machine translation like in general, right? You say maybe German, French, these are like a one. But is it possible to use the machine translation, even Google Translate also using, can you use the Kashmiri language? Because today nobody is actually typing in a Kashmiri, right? Maybe people may be speaking, but may not be actually having the data. So that means the dialects and everything, they are so different, the kind of usage. So that means you need to develop a different layers out of it, on top of it. You got it?
Yes, sir.
Yeah.
Yes,
Good
sir.
answer.
Yes, sir. Thank you. Thank you, sir.
That's the 2 ways that we are using it here.
So, as we conclude this enlightening guest lecture, I'm honored to deliver the vote of thanks on behalf of organizing committee. First and foremost, I extend our heartfelt gratitude to our distinguished guest speaker, Dr. P. Radhakrishna Garu, for sharing your valuable insights and expertise with us today. So your knowledge and experiences has provided us with a wealth of information and inspiration, sir. So we are truly honored to have you had here, sir. Thank you so much, sir.
Thanks everyone. Thanks everyone.
So here our guest lecture to us, Mr. Naga Brahmachari Pesarapati. So it is our privilege to welcome Mr. Naga Brahmachari Pesarapati as our guest speaker today. Mr. Chari is seasoned software engineering professional with over 15 years of experience and currently serving as a principal software engineering at Dell Technologies USA with extensive expertise in both UI and back-end development. Mr. Chari has designed, built, and tested, launched a variety of applications throughout his career. His contributions to automating testing tasks and enhancing process efficiency demonstrate his technical ingenuity and problem-solving skills. In addition to his technical expertise, Mr. Chari is an exceptional team player and a leader, having guided projects to successful completion and mentored team members to grow in their careers. He is committed to delivering reliable software solutions while staying updated with the latest tool and methodologies in ever so evolving field of technology. So we are excited to have him share his insights and experiences with us today. Sir.
Okay, hi.
Over to you.
Thanks everyone. Thank you. Thank you for introducing. This is Naga Brahmachari Pesarapati. I hope everyone is doing good. Good morning and good evening, everyone. So I'm gonna share my screen. Just give me a second. Okay, let me know if you guys started seeing my screen. Okay, all right.
Yes, sir.
So yeah, so today I'm gonna talk about large language models. So yeah, about myself, as you mentioned, my name is Naga Brahmachari Pesarapati. I go by Naga. So I'm working as a principal software engineer at Dell Technologies. So I'm currently located in Lafayette, Louisiana. So I have been handling almost from 15 years, like several technologies, UI, backend, and all the stuff like Java full stack. And I used to lead a team and helping helping juniors to onboard, so several things. So that's about me. So let's jump on the topic today. So we will go over introduction and understanding LLMs, significance in NLP, technical deep dive, challenges and ethical considerations, and future directions, and Q&A session. Maybe I'll show a couple of other diagrams also, if time permits. Yeah, let me know in case if any doubts or any questions in between also. So yeah, thank you. So introduction to the language, large language models, LLMs. We call them as LLMs as a short form. Large language models are advanced AI system trained on enormous data sets to understand and generate human-like text, built on deep learning architectures and particularly transforms. Examples including GPT, Bird, and ChatGPT. So these LLMs are AI systems that use advanced deep learning techniques to process and generate human-like text. They are trained on massive data sets, sometimes consistent of billions of words, to perform a wide range of language-based tasks. A common example is ChatGPT, which might be have been using and asking for several questions and get assistance with the writing and even coding debugging. So similarly, like Bird, also be a search engine to improve query understanding. So LLMs are not just a buzzword; they power tools we use every day, from conversational AI like Alex or Siri to business tools for text analysis. LLMs have become dispensable. By understanding LLMs, you will be able to appreciate how these models impact both technology and also our daily lives. You might even find ways to incorporate them to your work. So the evolution of NLP and LLMs. Early systems were rule-based, relying on the predefined grammar rules. Transition to statistical methods improved efficiency with the probabilities. Introduction of deep learning revolutionized NLP tasks. Transformers like GPT, Bird marked as significantly. So initially, NLP relied on rule-based, as I mentioned, where developers manually defined grammar rules. While effective for structured tasks, these systems could not handle complex or ambiguity. The next step was statistical models, which used probabilities to predict text patterns. These models improved accuracy, but we are still limited in understanding the context. So deep learning introduced natural networks, enabling models to learn from the data rather than relying on the predefined rules. This was game changer of NLP. So the transformers revolutionized NLP with their attention mechanisms, allowing models to process large amount of text while understanding context better. They paved the way of LLP like GPT and Bird. Key characteristics of LLMs trained on vast and device datasets, ability to generate coincidence, context evidence test, multi-language capabilities, leverage attention mechanism for contextual understanding. So LLMs are trained on massive datasets, often comparing books, websites, and other text sources. This enables them to understand a wide range of topics. These models can generate text that feels human-like and contextual appropriate, which is why they excel at tasks like writing and summarization. LLMs can understand and generate text in multiple languages, making them valuable for global applications. By focusing on relevant parts of the input, LLMs can handle the complex sentences and also maintain the content over long passages. Architecture of LLMs. The core component, attention mechanism for understanding relationships in data, encoder decoder structure used in some models, self-attention and functional embeddings enable sequence compression, scalability through parallel processing. Transformers rely on the attention mechanism, which helps them focus on relevant parts of the text while ignoring irrelevant information. Some bots like Word use the encoder to understand the text. Others, like GPT, use the decoder to generate the text. The combination of both enables the comprehensive language task. The self-attention allows the model to evaluate the importance of each word in the context of the sentence, ensuring better comprehension. Transformers can handle large data sets efficiently, making them ideal for training LLMs. Significance of NLP. Redefining tasks like summarization, translation, and sentiment analysis. Driving conversational AI systems, example virtual assistants, improving assistance through text to speech and also the language tools too, extracting insights from the understanding data sources. LLMs excel at tasks like translation, summarization, and sentiment analysis, delivering results that we are previously unstatable. Tools like ChatGPT enable natural human-like interactions, making customer service and virtual assistants more effective. LLMs power text-to-speech tools, helping people with disabilities interact with the technology more easily. LLMs analyze social media posts, reviews, and other data sources to extract valuable insights for the business. Realized NLP tasks, example, mission translation, text summarization, and sentiment analysis, how LLMs outperform traditional NLP approaches. Conversational AI, examples like chatbots like ChatGPT, virtual assistants like Alex or Siri. Real world impact, better customer service and personalized interactions. Accessibility enhancements, text to speech for the people who disabilities, real time translation, transcripts for tools for the meetings. Insights from unstructured data used in social media sentiment analysis, market research, and feedback mining. Domain specific streamlining. Applications in healthcare, summarization, patents, records, or finance analyzing financial reports. Applications of LLMs. Chatbots for customer support and virtual assistants, mission translation for global communication, code generation and debugging for developers, personalized learning systems for education, business intelligence tools for the sentiment analysis. Used in customer services to provide quick and accurate responses, real-time translations tools powered by LLMs improve global communication. From writing articles to generating code, LLMs save time and effort. Business use LLMs to gauge the customer sentiment from the reviews and feedback. Chatbots for the customer support, automated real-time support. With this, we can reduce the workload for human agents while improving the response time. Mission translations, tools like Google Translate are deeply importance of context awareness, aware translations enabled by the LLMs, content generation, articles, blogs, posts, and creative writing, and code generation for the developers, example like GitHub, Copilot, and other tools. Sentiment analysis, extracting customer sentiment from the reviews or social media. With the help of this, helping business make data-driven decisions. educational tools like personalized learning platforms powered by AI, example, Duolingo AI-driven courses, medical applications summarizing lengthy research pages, support to diagnostics with natural language understanding, technical deep dive. Attention mechanism identifies the key information in the input. Contextual embeddings capture the meaning of the word in the context. Key advantages GPT for generating task, Bird for understanding the task. Difference between model based on their training objectives. Okay, this helps model focus on the most relevant parts of the text, encodes the meaning of the word based on their context, improving accuracy. For example, GPT is generative while Bird is designed for understanding tasks. So if you see here, attention mechanism explains how the model determines which words or phrases are most relevant. So it will help us to understand the complex language structures. Contextual embeddings represents the meaning of the word in the context. Example, Apple in I ate Apple versus Apple is a tech company. So that's how it will differentiate the meaning of the words in the context of the sentences. GPT versus Bird. GPT generates the text by predicting the next word in the sequence. Bird understands the context bidirectionally, excelling at a comprehensive task. Training data processing. Tokenization, breaking text into smaller units. Data cleaning, removing irrelevant or noisy information. Fine tuning for specific tasks. Adapting pre-trained models for specific applications like healthcare or finance. Challenges and ethical considerations. High conceptual resources requirements. Potential bias inherent from the training data. Ethical concerns around misuse and misinformation. Need for transparency and interoperability. LLMs require significant computational power and storage. Training data can introduce bias leading to the unethical output. The black box nature of LLMs makes them hard to interpret. So high computable costs like LLMs require significant hardware like GPUs, TPUs, and energy. As I mentioned earlier, bias in training data, models can reflect and amplify the bias present in the data. Ethical concern, potential misuse in the creating fake news, deepfakes, or spam context. Transparency issues, LLMs often operate as black boxes, making it hard to interpret decisions. Balancing innovation with regulation, importance of creating policies to ensure responsible use. Future directions, enhancing efficiency through models optimization, developing domain-specific LLMs for specified tasks, addressing ethical and social impacts of AI, expanding real-world applications across the industries, optimizing models to reduce resources consumptions, adapting LLMs for specified fields like healthcare, developing guidelines to ensure fair and responsible use, model optimization, reducing the resource footprint of LLMs for wider accessibility, ethical AI practices, developing frameworks to identify and migrate biases, domain-specific LLMs, trialing models for specialized tasks in fields like healthcare, law, or finance, enhancing real-time applications, use cases to robotics, AR, and virtual realities, collaboration with policymakers, establishing guidelines to address ethical and social impacts. I'm going to share another document with a couple of diagrams. So these are the couple of where LLM era is random shift to machine learning. If you see here, representation of BERT in 2018 and GPT June 2018 generation. So how this data inputs takes and how it is generating the output. So this is the another one. So GP2 generalization to unseen tasks, like LMs used to different tasks by pre-trained base model and then fine-tuning for the tasks of interest. Political issues, too many copies of model, need for large-scale labeled data for fine-tuning, can do only specified tasks. GP2 generalizing unseen tasks. LMs can be used to different tasks by pre-trained and base model and then fine-tuning for the tasks of interest. Political issues, practical issues, too many copies of model, need for large-scale labeling data for fine-tuning. Multitask training, data remains as a challenge. Humans don't need such large volumes of data to learn, can do better. Train a model that can perform NLP task is a zero-shot manner. GP2 task specifications. Primary shift comes from modeling assumptions from single task to general model. Task specifications. Primary shift comes from modeling assumptions from single task to general model. Task describes may be provided as a text. For example, translates this French text to English. So what makes such as a LM work? Diverse training data models can do many disparate tasks with no training at all. Scaling model capability and data. Below are the few statistics that we can see here. Scaling in GP2. Scaling improves the predictability of the LM and improve performance. If you see here, this indicates the performance of the GP2 scaling. Why this is interesting? Look at the data scaling. We know the typical scaling efforts look like this when we increase the amount of training data. So why this is interesting? Look at the data scaling. Loss and the data sets size is linear on the long plot, and this power law scaling. And if you see here both diagrams, like this is the training data set for long scale, and this is the data set size as a tokens. The scaling, we can understand scaling by posting scaling laws. With scaling laws, we can make decisions on architecture data, hyper parentheses by training smaller models. We have a couple of references here. So the key findings are performance depends strongly on scale and widely on the model shape. Larger models are more sample efficient, smoother power law. Scaling efforts. The effort of some hyperparameters on big LMs can predicted before training. Optimizer, model depth, LSMTM versus transformer. The idea is train a few smaller models, establish a scaling law, select optimal hyperparam based scaling law prediction. So model scaling GP3. This is the diagram for model scaling GP3. So emergent abilities with GP3. The emergent abilities not present in the smaller models, but present in the larger models. Do LLMs like GPT have these findings? GPT-3 trained on text can do arithmetic problems like addition, subtractions. Different abilities emerge at the different scales. Emergent abilities with GP3. So this is GPT trained on text can be arithmetic problems like addition, subtractions. Different abilities emerging at the different scales. So these are the different versions we are seeing here. So in this version, GPT-3 trained on text can do arithmetic problems like addition, subtractions. Different abilities emerges at the different scales. Model scale is not only the contributor to emerge for 14 big bench tasks, Lambda 137B, GPT-3 models perform at near random, but Plum 62B achieves above random performance. Problems LLM can solve today may be emergent for future LLMs. Large scale models that have many parameters over and can perform multiple tasks through prompting. Examples GPT, Lambda 2, Gemini, Plum, Mistral, Extra. LLM realization architecture. We have three different architecture like encoder, decoder. Encoder is only for example is word, pre-training, masked language modeling, MLM, great for classification of tasks but hard to do generation. Decoder only, GPT, pre-trained auto-regressive language modeling, stable training, faster coincidence, better generalization after pre-training. Encoder and decoder, pre-trained mask spam prediction, good for tasks like MT and summarization. Masked spam prediction. Masked spam prediction involves masked continuous set of tokens in input, predicts this masked spam for the decoder. The attention patterns. Casual decoder, each token attends to the previous tokens only. In both non-casual decoder and encoder and decoder, attention is allowed to be bidirectional on any conditioning information. For the encoder decoder, that conditioning is fed into the encoder part of the models. So a couple of observations here. Decoder only models outperform encoder decoder models using similar configurations. These are the configurations statistics we can see here. Lambda 2 architecture. Decoder only models. Changes in transferring models. Norm after sublayer. So a couple of equations here like position, embedding, long context, activation, layer norms, all these we can see here in the diagram also. So these are the couple of poles we have. I'll skip this maybe. So supervised fine-tuning versus pre-training. So objective functions loss computed only for the target tokens in SFT. All the tokens are targeted in pre-training. Input and targeting. Instruction plus input as input with target in SFT, and only input as input with shifted input as target. The purpose is pre-trained makes good generalist auto-completes, but good SFT builds models that can do many unseen tasks. SFT can also guide nature of outputs in terms of safety and helpfulness. Introduction tuning. So these are the couple of tuning techniques. Sample example for this. Unsafe outputs alignment problem. LLMs may produce harmful text, unparalleled language, bias and discrimination. Text that can cause direct harm, allowing easy access to dangerous information. Therefore, LLM should be trained to produce outputs that aligns with the human preferences and values. Modern LLMs do so by using SFT and by using human preferences directly in the model training. Training of decoder only LLMs, Llama 2. Auto-regressive pre-training, trying to predict the next token on very large scale, Copera, almost 3 million tokens. Instruction fine-tuning, supervised fine-tuning, which we call as SFT. Fine-tune the pre-trained model with pair of instruction plus input and also the output with large data sets, and then with a small high quality data sets. Safety and RLHF. Design a reward model based on human feedback and use policy guarantee methods with the trained reward model to upgrade LLM parameters so that the output aligns with the human values. These are the few scenarios in RLHF. If you see here, step 2, step 3, here it is collecting comprehensive data and train a reward model. On the same line, optimizing a policy against the reward model using deferment learning. A prompt and several model outputs are sample-wise. Here they are processing the one of the requests. Explain the moon landing to a 6 years old. So this is how they'll explain it. And a label rank that outputs from the best to worst. If you see here, by comparing all the results, it will provide the best to worst. This data is used to train our reward model. So this is how it's being fed to the model. And in the other hand, the new prompt is sampled from the data set. So they collected, like, write a story about frogs. The policy generates the output and generates an output. So this is how it got generated the output. And the reward model calculated a reward for the output. The reward is used to upgrade the policy using PPPO. So this is how it got the result. So this is the comparison for RLHF. Model fine-tuning for RLHF. Next token prediction with the LLM. Reward model structure. So we can see here the comparison between these two. It looks almost same, but the processing is a little different. Here they'll use token-based probabilities, but here human preferences, annotation. Notes on the LLM safety and harmfulness. Does doing RLHF and safety tuning means LLMs will never produce harmful outputs? Note on the LLM safety and harmfulness. So the answer is no. The list of harmful outputs is not as large as this one. What is the other concerns? Adversarial robustness. Adversaries can force the LLMs to produce harmful outputs by attacking the model. In our experience, cloud produces harmful outputs that least when compared to the models like ChatGPT and Llama. So one of the four here, which of the following is the feature of LLM2? So we see here the output of this particular poll would be group driven query attention. So the LLM prompting. So the prompt tell the model what to do in the natural language. For example, generating a textual summary of the paragraph can be as short or as long as required. Prompt engineering. The task of identifying the correct prompt needed to perform a task. General rule of thumb, be as specific and descriptive as possible. Can be a manual or automatic, pre-text tuning or paragraphing, etc. So this is the one of the example for ChatGPT prompt, where we can see here the model is here role, name, and the context. So in this context, providing free samples along with the instructions. Instruction is please specifying. So one of the example, movie reviews as positive or negative. Input, I really don't like this movie. That is a negative prompt. And this movie is great. That is the positive prompt. Chain of thought prompting. Get the model to work through the steps of the problem. So this is the standard prompting and this is the chain of thought prompting. If you see here, first they are asking the question. In the standard prompting, directly it is answering straight to the answer question. But here, if you see here, chain of thought prompting, the connected question is being answered with explanation. So the chain of thought prompting enables the large language models to tackle the complex arithmetic, common sense, and symbolic reasoning task. Chain of thought reasoning process are highlighted. Sorry, excuse me. So these are the couple of examples we can see here. So note on the parameter efficient fine tuning. When we don't have large enough data for SFT, freeze the LM and keep some parameters for trainable. Add an external sorry. Add an external adaptive model to adapt the model parameter to task. Perform low rank adaptation. Evaluating LLMs. Evaluation is challenging. Evaluating on as many data sets on the task as possible. These are the few benchmark statistics we can see here. So this is the comparison to the closure source models on the academic benchmarks resulting for ChatGPT 3.5 and ChatGPT 4. These are from the OpenAPI 2003 model. Results the PLAM model from 2022. Results for the PLAM are the NTL. So these are the statistics benchmarking. Multimodal LLMs. Text is the only part of the picture. We want LLMs that can understand the word by seeing and listening as well. Model should be able to do cross-modeling, reasoning, and learning. Multimodality can be introduced from pre-training. One of the example is Gemini. From instruction tuning, Audio GPT and Flamingo. Model data using continuous representation. Using continuous speech representations, we have a couple of pros and cons. Rich information, good performance is the pros, and computationality heavy and storage heavy. If you see here, the speech LM having the modularity encoding, speech encoder plus text enabling and text tokenizer. So modeling data using descriptive units. Recently, descriptive units shows promising performance and benefit. So these are the couple of configurations of that particular model. Modeling data using descriptive unit. So as we have seen this diagram, speech LM will be connected to the token embedding. The token embedding text vocabulary and the speech vocabulary, both are processing, and we have a speech quantizer and a text quantizer, text tokenizer. Multimodal LLMs representing images. Continuous embedding, concatenating with the embedding of text input to the LLMs. Pre-trained independently, example clip. Descriptive representation extracted from the self-supervised audio models like VQ, VA, EASE. So a couple of challenges with LLMs. New capability, multimodal, multilingual, more complex task. Performance, reduce limitations, improve alignment with human preferences, increase context length efficiently, improve data and training strategy and model architecture, efficiency, conceptual cons, time and model, compute architecture, GPU, TPU, HPU, and safety, reduce harm, improve heterogeneous robustness, privacy concerns, interoperability. Why do we LLMs do what they do? So this is the overall summary. LLMs are large-scale models that possess uh, astounding abilities. Scaling both data and model capacity is the important for performance and leads on the emergence of our new abilities. Decoders only architecture are popular for convergence and performance. LLMs are trained using pre-training SFT RLHF. LLMs are evaluated using prompting strategies like ICL and COT. multimodal LLMs can process audio, text, images, and more. So this is all I have. Let me know if you have any questions. Yeah, I'm done with my presentation today. So yeah, let me know if any questions I can answer.
Any questions, participants?
So in the real time also I can share, one of my experience also, like, as I mentioned, these LLMs can help us, wide range use every day in our daily life also. So in our day-to-day work life, so we used to send emails, large emails. So for that we can, feed the or use any models like ChatGPT or Bird or anything. So if you, it will be, summarizing our emails, or, correcting all the grammar or anything. So we can use that for our email, replying emails and all. And also task prioritizations, like every day in our day-to-day activities. So I think, so we used to have a lot of tasks. So by providing all the tasks and the importance of the task, it will segregate and list it down and, summarize all the things. So that is another thing we generally used, as it is a real-time experience for me. And not only for that, any other any other suggestions or anything, like, let's say if you went for some medical tests, and you got some blood test, and you got the report, but you don't know, like, I mean, you haven't visited your doctor, but you just wanted to know what happened, or what are the details of that particular stuff. So you can simply, by uploading, example, chat GPT, maybe by uploading the report, you can ask for the details, so that it will be explained by decoding all those data with help from the file. And it will provide the data just like understandable data. So yeah, likewise, I mean, many use cases we can use every day-to-day activities. As a professional, like, I would say, like, almost from couple of years, like 3 to 5 years, we started using chat GPT or Bird, or so many other AI tools. And we do have even company based AI tools for specific tasks, like holding the code, GitHub, or so they have developed their own, each organization are investing a lot of money to build their own AI tools. So yeah, that's another thing I just want to share with you all.
So, as we conclude this session, I'm honored to deliver the vote of thanks to our guest speaker, Mr. Nagabrahmachari Pesarapati. So, sir, we are deeply grateful for the valuable insights and experiences, sir. Please accept our heartfelt thanks for your presence, presentation, and willingness to share your knowledge with us, sir. So, we privileged to have had as our guest speaker, and we hope to you have back with us soon, sir. Once again, thank you, Mr. Chari, for your enlightening and engaging session. We wish your continued success in your endeavors.
Yeah, thank you so much, Swati, and thanks for this opportunity. So yeah, have a
Thank
great
you,
day.
sir. Thank you, sir. Thank you, participants. And we will meet tomorrow at 6 p.m. again.
Thank you, madam.
Hello, good evening. We will share the feedback in the WhatsApp group, and all of you will be give the feedback in that group. Is mandatory to all.
Okay, sir.
Thank you.